get the recording going. All right. So, let's go ahead and get the screen share, and we'll go ahead and hop into it and start talking about Newton's laws of motion and free body diagrams and all that fun stuff. So, first thing I want to know is, what are Newton's three laws of motion?
I got them mixed up, but I know one is like force equals mass times acceleration. One is like every action has an equal and opposite reaction.
Mm-hmm.
And um, I think I forgot the last one. Was it just like the one about energy? Think wait, that's a different thing. So
So, you said something about F equals ma. So, do you know which law that is? Is that the first, second, or third law?
I think that's the first law.
It's actually the second law,
Oh,
but
that's the second law. Oh,
it really doesn't matter. Like, I'm gonna keep it a buck 50. It really doesn't matter as long as you understand and are able to work with all three. And the one law you're forgetting is honestly, like, it really doesn't matter too much, and you don't really. It's usually pretty, like, I guess it's one of the simpler things to understand conceptually. As you mentioned, F equals ma. That's Newton's second law. It's the law that essentially dictates it's the relation between a force and an acceleration on an object. And then we have, you said every action has an equal and opposite reaction. Essentially, we'll call it F12 is equal to negative F21, just then in the opposite direction. So essentially, like, if I push against a wall with a certain amount of force, the wall is also pushing back with the same amount of force on me. Or if you're standing on the ground, I mean, for example, for me, I'm standing on the ground. I'm a big boy. I weigh about 260 pounds. It's about 115, 116 kilos. So I'm exerting about a little over 1,000 newtons of force on the ground. The ground is exerting that same force back up on me. And then the third law, or that was the second and the third law. The first law, the last law remaining, the third of the three, but the first, whoosh right over your head, is the law that dictates how objects, how their motion changes when there's no net force acting on them. Have you heard something about how objects will remain in motion until acted upon?
oh yes.
Yep.
I
So
remember.
that's Newton's first law, where essentially an object that is in motion will remain in motion until acted upon by some sort of net external force. Essentially, no force, no acceleration. It's basically a derivative of the second law, where if I guess the best way to sort of write the first law is if F equals 0, A equals 0. Basically, constant speed, motion, constant velocity will stay that way forever until some sort of net external outside force acts. Those are Newton's three laws of motion. And reality is, they're not too complicated. They're pretty simple to understand and work with, and they're usually not too much of a holdup for a lot of students. Main thing is just getting comfortable with understanding Newton's third law of motion, I think. That's the one that sort of conceptually doesn't make a lot of sense for people. So, the other thing we want to know is, what is a free body diagram?
Oh, that's just like when we draw all the forces acting upon an object, right?
Mm-hmm. So, for example, if we wanted to go ahead and draw a free body diagram for, let's go ahead and we'll have like me standing on the ground and there's a box. We want to draw the free body diagram for a box. I'm pushing on the box. What are going to be, and it's all on the ground right now. What are going to be all the forces acting on this box?
So there would be the weight going downwards and then the normal force going upwards with the same.
Exactly.
magnitude,
Exactly.
and then would be the force of the push going towards the right.
Mm-hmm.
And if there was friction, then we see that going towards the left in a smaller magnitude.
Yep. Exactly. So we have the normal force, we have the weight, which is equal to the mass times gravity. We have our force, we'll just call it F, and then we have our frictional force, we'll call it small f. And using these free body diagrams, we can understand the total net amount of force acting on the object at any point. And if we know the net force and the net direction, we'll know how the object is going to accelerate. So, what if I were pushing the block along at a constant speed? How would this free body diagram change?
F net would equal to 0.
Mm-hmm. So what would happen so that F net was 0?
Would the friction force and the force of the push be the same?
Yep, exactly. If I'm pushing along at constant speed, it means that whatever force I'm applying is going to be equal to the friction force that is stopping it from accelerating more, and creates a net zero force, which means constant speed, constant velocity. So one more thing we want to know is, how do we calculate a friction force acting on an object?
Well, if the object is at rest, then um, I know that there's those two equations that we use, which is like the friction coefficient and then the times the force.
Mm-hmm. So
But it's different for when it's in motion and when it's not.
So what if an object is at rest? How do we calculate the friction force acting on it?
It would be the friction coefficient for I forgot what the word was. The friction coefficient for when it's is it static?
Yep, exactly. The coefficient of static friction. It's not moving.
Then times the weight.
Mm-hmm. Right. Not specifically the weight. It would be the weight if you're on a flat surface, but what if we're on an angle?
Oh, then it would be the um the force that it's going at the angle.
Could you repeat that? You can sort of cut out.
Or would it just be like the force that it's going at the angle? So if it's but it's at rest, it's not moving. Oh, the normal force?
Exactly, the normal force. So it's whatever force is acting up on the box from the surface that it's on. So if we're on a flat surface, that is just the weight. It's just mg. But if we're on an incline, then our normal force isn't going to be equal to the weight because the weight is pulling down. But we know the normal force is going to be obviously normal to the surface in such a way that it ends up balancing out everything and we get no net force, essentially, if it's at rest. So we have so you said it's the coefficient of static friction times the normal force. Now, so what happens if, for example, our coefficient of static, let's say we have a 1 kilogram box, so it's a 10 Newton box, essentially. That's the normal force is 10 newtons. And the coefficient of static friction is like 0.5. So essentially, it would take a 5. We have a coefficient. We have a frictional force of 5 newtons, right?
Yeah.
So what if I applied a 2 Newton force to the box? What would happen? So if we have our box, we have the normal force up, we have the weight down, and we apply... What?
Oh, it wouldn't move?
It wouldn't move, but... So we were applying 2 newtons here, and we calculated our friction force as 5 newtons, right?
Yes.
So, but that would mean there's a net force, and therefore a net acceleration, right?
Oh, yeah. Because they're not equal.
So that's clearly not the case, because we know the box isn't going to move. Clearly something's wrong here. I took a look more specifically at the formula sheet itself.
It's not equal to, right? It's less than or equal to, so I guess in this case it would just be the same as the force of our push.
Exactly. So our static frictional force, a little, Fs, is always going to be our. So I'll actually go ahead and write this. We have our static frictional force. Fs is always going to be less than or equal to the coefficient of static friction times the normal force. So essentially, our static force is always going to be equal to our applied force up until its maximum possible value, which is the 0.5 times the normal force. And then the box would actually begin to start moving, and then we have to worry about kinetic friction, right? Is that the same kinetic coefficient of friction, or is it different?
It would be a different coefficient.
Is it going to be bigger or smaller than the static friction coefficient?
It should be smaller.
Why is that?
Because when it's in motion, it'll be harder to stop. Is that wrong?
I guess it's sort of right. I mean, obviously, like you might have had this experience where if you're trying to push something along, if it's at rest and you like try to push it, it takes a lot of force to get it to start moving initially, because you have to break that initial static friction maximum point to get it to start moving. But after that, once it's already moving, it doesn't take as much force to move, because it's already in motion. So the kinetic coefficient of friction is always going to be smaller than the static coefficient of friction. All right. So let's go ahead and do you have any questions about this so far?
Oh no, it makes sense.
Yeah. You seem like you understand it pretty well. It's just that you like forget like one little thing here every now and then, or maybe you knew it but you didn't realize I was asking for it. So let's go ahead and hop into an example problem. So we're going to have a 4 kilo block. It's going to sit at rest on a 10-degree incline. So we're going to have, let's say not quite to scale. We're going to have a 10-degree incline. We have theta, which is 10 degrees, and we have our block sitting at rest on the incline. Am I able to rotate this? I don't think so. I'll draw it with little lines like this. So we have our block sitting at rest on our incline. So let's go ahead and actually draw a free body diagram of the forces acting on the block, and also calculate the normal force acting on the block from the plane, as well as the frictional force. It'll take 10 minutes, then we'll talk about it. So we want the free body diagram and then actually calculate the normal and frictional forces holding it at rest. Great. In that case, let's go over it. So, what is our free body diagram of our forces going to look like?
It's gonna be so like a dot in the middle, and then there's gonna be the weight force going straight downwards.
Yep. I'm actually going to go ahead and draw it over here on the right, just to make things easier. So we have our center here. That would be like our block. We have our weight going down. Right.
Then we would have the normal force going like towards kind of like at the same angle that the box is at, going upwards.
Yep, something like that.
And then the friction force would be going towards the right, also at the same angle as the incline.
So like this.
Yes.
Is that the case? Is the friction force going down to the right, or?
I guess in this case, well, could be going up to the left as well. Oh, because it's not in motion, and it's stopping it from sliding back down.
Exactly. So our friction force is going to be up and to the left because we know it is holding the block in place. Like, we would think naturally the block is going to want to slide down to the right, so the friction force is acting against that up to the left. So how do we go ahead and actually calculate our normal and friction forces? Take me through your process.
So the normal force is at an angle, so it wouldn't just. So I'm guessing I would multiply like the weight force times the angle that it's at.
So we have the weight force times the angle, or explain to me how you got that.
So I made like a little. Sorry. So the weight force. Okay, so let me see. Okay, so the weight force is at an angle, and so I could like put it into like a little coordinate on its own to sort of see that it's sort of like the hypotenuse of like the questions that we did in class last week.
So you're creating a new coordinate system at that slight angle, something like this?
Oh,
Is that what you're doing?
no, I just made it like a regular coordinate system at that angle, with that angle shooting out of it.
So you're like treating it as if something like this, where the normal force and the friction force are, or are you breaking the normal force into x and y components?
I was breaking the normal force into x and y components.
Oh, okay. So we have our x and y here. I'm breaking the normal force into boom, boom. So continue.
guess I did this kind of wrong. That was my uh actually do okay, I see. I think I did this a little bit. Then if the
You're like cutting in and out here. I heard you say you think you did this a little. 3 seconds of
I
silence.
think I did this kind of off. Now that I think about it, because it's not at a straight angle, it's going downwards. Oh, but then in order to find like the hypotenuse, which would be like my bad, the way that the normal force is going, hmm, that would be. Oh, I see. So if I did it that way, then I would have had to do cosine of 10 instead of sine of 10, which is what I did, because the that triangle is not the same as the triangle below it.
Mm-hmm. So yeah, because this angle here would be our 10 degrees.
Yeah. Oh,
So
because what I originally did was the weight times the sine of 10, but I see I drew my triangle wrong.
the weight? I thought you were breaking the normal force.
Oh, yeah. Oh, shit. Yeah, that's not the same thing.
Well, I'm going to go ahead and sort of stop you here, and we're going to backtrack real quick a step or two, because I think the way you're doing it here, where you're using actual x and y axes and breaking the normal force in x and y components, and you would also have to break um, the frictional force in x and y components, and it's going to be a lot more work, and it's going to be a lot more annoying to actually calculate the normal and friction forces. I would recommend create a new, x prime and y prime axes at our 10-degree angle. So we have our x direction, which is angled down to the right, and our y direction, which is angled, here, so that our normal and friction forces are in line with them. And then we only have to break the weight into our x prime and y prime directions.
See.
Right?
Yeah.
So which angle here is our 10 degrees? This one? So 1 or 2?
It should be 2.
Yep, exactly. So we have our 10-degree angle here, theta. So what is the y prime component of our weight?
Um, 6.9927.
Oh, you actually calculated it?
Oh,
So,
yeah.
um, would that be right?
It would be. Oh. Okay. Oh, I see.
Well, let's think of it this way.
That's already our weight.
We have our weight, and we know obviously that whatever our y prime component of the weight is, right here, we know it has to equal the normal force, right? Because we have 0 net
Yeah.
force. And then the x component has to be equal to the frictional force, because once again, 0 net force. So we can say that the normal force is equal to the y prime component, which is the weight, which is mg times sine is opposite, cosine is adjacent. This would be mg cosine theta. And then our frictional force, Fs, is going to be mg sine of theta. Right? I think you might have had cosine and sine mixed up here.
Yeah, I did them reversed.
Yeah. So then all we need to do is plug these in. Mass is 4 kilograms, so we have mg is 40 times our cosine of 10. We get a normal force of 39.4. 39.4 newtons. And we have our times the sine of 10 degrees, we get our 6.9 that you had found. But that's the frictional force. So the way you did it, obviously you were able to get one of the two correct values. It's just you got them mixed up because you just need to work a bit on your trigonometry, but also you probably also got mixed up because you were essentially forcing yourself to do extra work by using the actual x and y coordinates.
Let's see.
Because this way you literally just break down the one thing and you know it's equal to the normal force and the frictional force. Just break down the weight into x prime and y prime. You have any questions about this?
No, it makes a lot more sense than what I was doing.
Yeah, I mean, clearly, were you able to calculate, your normal force? You calculate 6.9. Did you get the frictional force of 39.4?
Yeah, I got those numbers. Just
You just got them
I
mixed
had
up.
labeled them. Yeah.
Yeah. So yeah, I highly recommend use the different coordinates because then you're just doing less calculations, so it gives you less opportunities to mess up, and that's usually a pretty good idea. Try to minimize the chances you give yourself to mess up on your quizzes, and it usually works out pretty well. So let's go ahead and increase the degree of this incline. So we're going to slowly tilt this thing more and more and more upward until eventually the block is going to begin to slide. Now, we know the coefficient of static friction is 0.5. So what angle would the block begin to slide? I'll give you a few minutes and we'll go over it. Let me know when you're done. So let me know, how did you get that? Take me through your whole process.
So from the previous... So the formula says that the static thing is times the normal force equals oh, I did that backwards. Oh no, wait. Yeah. Equals the friction force.
So repeat that.
Oh, so I used the two things that we got the two values that we got from the last problem, and sort of did like so the equation, like the friction static force equals like the friction coefficient times the normal force. I
Mm-hmm.
plugged in the friction coefficient and normal force, except I didn't plug in this. That seems a bit backwards. I didn't plug in the angle for the friction coefficient. I just did 40 sine of the angle equals the friction coefficient times the normal force.
What normal force did you use?
I used the same one from the last problem.
The 39.4?
Yes.
Well, would that be the case? Because wouldn't the normal force change as the angle changes?
Yes, I forgot to take that into account.
So how would it change? How did our normal force change as the angle increases?
As the angle increases, it would get my measurements. It would get smaller, right?
Yep, and why is that? How do we calculate it as it increases? How do we calculate it for any angle?
Well, the way that we did it in the last problem was mg times cosine of theta. And
Yep.
the angle that's at that position would slowly get smaller as the other angle increases.
So we know the angle increases, so as the angle increases, cosine of theta is going to decrease. So you said something about our frictional force is equal to mg sine theta. He said 40 sine theta. So
Yes.
we'll say mg sine of theta is equal to our mu sn, right? Our maximum frictional force. This is the point at which it will start sliding, which if we go and plug in our normal force of mg cosine theta, the mu s mg cosine of theta, right?
Yes.
So now we can go ahead and calculate our coefficient of friction by, we can cancel out mg on both sides. And so then we have mu s is equal to, we have sine divided by cosine, so tangent of theta. So then theta would just be the inverse tangent of the coefficient of friction. Right?
26.5. Yes.
It would be 26.5?
Oh, yeah. 4.6.
Yep, 26.5, 26.6 degrees. Boom. Nice and easy, right?
Yeah.
You just, it's actually really, I find it really cool how these things sort of, magically fall into place, and the masses cancel out, the gravitational constant cancels out. It really literally doesn't matter. So you could have this block and this sloped incline on literally any planet in the solar system. It doesn't matter. The gravitational constant doesn't matter. The mass of the block itself doesn't matter. All that matters is the coefficient of friction. And that's what dictates what angle the block will begin to slide. So I think that's pretty cool. I don't know. Maybe I'm just geeking out about that.
Pretty convenient in terms of
Yep.
calculating.
So how would we go ahead and calculate our coefficient of friction if instead of being given the coefficient of friction and finding what angle the block begins to slide, what if we are given the angle it begins to slide? How do we calculate the coefficient of friction?
We could just plug it into the same equation, right? So do mg, then if we're given 18 degrees and coefficient. Oh, yeah, just the same. Like mg sine of 18 equals to. You said it's called mu.
Yeah, mu.
So mu times the normal force, which would be mg cosine of 18.
Mm-hmm.
Which I guess they would cancel out again and get tangent of 18 is equal to mu.
Yep, exactly. We have our. So hold on, give me a second to sort of. We have our A, B, C, D, and then E. Yep, it's literally we do the exact same thing where we set them equal. We have mg sine theta is equal to mu mg cosine theta. Mg's cancel out. We just get mu is equal to the tangent of theta. So mu s is equal to tangent theta, which is equal to. Well, what did you say it was?
0.32.
Yep, about 0.32. And what are the units on our coefficient of friction?
I'm not sure. I forgot to write down the. I actually haven't written down any.
I may or may not be pulling a fast one. I may or may not be asking a trick question here.
Oh, I see. So would it be none?
Yeah, there are no units. It's a unitless quantity. It's just a ratio, essentially. It's a
Mm.
ratio that it's something that dictates the ratio between the friction force, the maximum possible friction force, and the normal force. So boom, that's pretty much it. That's pretty much all you'd need to know for, I mean, any like inclined plane, block, coefficient of static friction, then it begins to slide and all this stuff. So let's go ahead and I actually don't have any examples prepped, but we can just sort of make one up on the fly. Let's say our block begins to slide at our angle of 18 degrees. And let's say it begins to slide and it accelerates at, let's say, half a meter per second squared. What would be the kinetic coefficient of friction? I actually don't know if the value would be realistic. Like, it might be more than the static, but whatever. We're going to go with it. So we know that at 18 degrees, the acceleration is equal to half a meter per second squared. How do we get the kinetic coefficient of friction? I'll give you like 3 minutes and we'll go over it. Or just let me know when you're done.
Hold on, just 1 minute.
Yeah, you got something? You got something going? You got an answer?
I got an answer, but it seems a bit small to be correct.
Yeah, well, I mean, the
It's
thing is, I made up the number of the acceleration on the spot, so it's probably going to be something that doesn't make much sense, realistically. But the reality is, if we go through and we actually do the calculation, if the numbers check out, it checks out. So, take me through your process.
um. So the force of friction will always be like the coefficient times the normal force. So I did that first.
Mm-hmm. So we have Fk is equal to mu Kn.
I calculated the normal force using the same as that we did last time because I don't think that would change in terms of how we would get the normal force.
Yep, exactly. It won't change. It's still going to be mg cosine of theta, which theta is 18 degrees here.
And I got like 12.36. And then I wasn't sure about the other part, so since it's sliding down, it wouldn't be the force of gravity, right? It would be the force of acceleration that's tugging it down.
What force? What force would it be?
Um, it would be the 0.5 meters per second squared.
That would be the acceleration. So, how do we go from the acceleration to the force?
Just multiply it by the mass.
Exactly. So, we know that our total net force, F net, actually, I'm going to say the magnitude of our net force is going to have to be ma, which is equal to obviously 0.5 meters per second squared times the mass, which is going to be 2 newtons. So, how do we then get our coefficient of friction? We have our total net force. How do we get the coefficient of friction?
Uh, well, in order from like it would have to be like ma minus the force of friction, right?
Well, our force of friction is included in this net force here.
Okay, so
So we know our total net force. Obviously, our y prime direction is going to cancel out, so it's all in the x prime direction. We have our negative friction force plus something here, so that the total net force is 2 newtons. How do we get that net something?
Mm. It would have to be the force of. The only other force tugging on it would be like the force of gravity that's pulling it down, right?
Exactly. So what would that x prime component of the gravity force be?
It would be mg. Oh, mg's sine of.
Yep, exactly. It's going to be mg sine of theta.
Oh, okay. So that wasn't.
Yeah, it's
Okay.
really not that big a deal. It's not too bad, not too hard to understand. Because we know we just break down this weight into our x prime and our y prime components. It's the exact same free body diagram as before. It's just that our friction force we know is going to be smaller so that there is a total net force down to the right.
Okay.
So let's go ahead and write everything together. So we know that mg sine theta minus mu k mg cosine theta is equal to ma. We're just writing all this stuff together. Obviously we can see m cancels out from everything. And then we'll go ahead and we'll move this over to the right. So we have negative mu k g cosine theta is equal to a minus g sine theta. So then we solve for mu k. Mu k is equal to g sine theta minus a. Just move the negative sign over, and then divided by g cosine theta. We plugged it all into a calculator, and you said it was, what value did you get?
I got 0.05.
0.05. So we have 10 times sine of 18 minus a, which is 0.5, divided by 10 times the cosine of 18. I'm getting a value of about 0.27.
Yeah, I didn't actually. I guess I should have done that, but I didn't simplify the equation first.
You were using numbers along the way?
Yeah.
Yeah. I highly recommend do all the algebra first and then just substitute the numbers in at the end. At least, I mean, I'm biased because I am a physics major and I haven't actually used a number in one of my own homework problems in about 3 years. We always just leave things in variables and stuff. But I think the going through and actually doing all the algebra and using leaving everything in terms of just the original variables is a lot cleaner and easier to do rather than calculating numbers at every point and having to go back to your calculator 20 times during one problem. Why not just do everything on your paper, leave your calculator to the side until the very end, and then you just plug in the last little part here to calculate.
That does sound a lot easier.
Yeah. So where do you think you went wrong?
Or I guess I could see an obvious thing that I did wrong. Instead of doing mg sine at the beginning, I think I did. I think this is an a. Ma sine theta instead of mg sine of theta for the force, which is
for this part here.
yeah.
Yeah. Okay. So you used a instead of g. That would do it. I mean, just forgetting that a is the actual net acceleration of the block itself, and g is the acceleration due to gravity. But obviously, then the the normal force occurs and the friction force, so we end up, creating our net A down to the right. But yeah, do you have any questions about this?
No, I think I understand it a lot better now. I just need to go back and redo some things.
All right. Well, if that's it, don't have any questions, we'll go ahead and wrap up the session there. Thanks for popping in, and hopefully this helped out a bit.
Yes, thank you.
Yep. Same time on Thursday, 1:15, 1:20-ish. Depends on how long my 122 session I hold right before this goes over. I went about 10 minutes over today. I wrapped up at 1:10. I was just like, all right, I need at least 5 minutes to go pee and get some water. So
yeah.
So I gave myself a few extra minutes, but yeah, same time, about 1:15, 1:20 on Thursday, and we'll go over tomorrow's material. Right. Have a good day.
You too.
Bye.